talk about sources of isotopes in organic matter and how we analyze for them quickly. The source of carbon, of course, is atmospheric CO2 and the 13C value of it. The thing you do need to remember, and I think Jim alluded to this, is that it has changed. So going back to the 1800s, it was a little over 6.5 or under 6.5, and then it's dropped now down to the -8. So we have changed by burning fossil fuels the isotopic composition of the atmosphere. And you need to know this, and you need to correct for this if you're doing tree rings way back here. You have to know that. And there are, you get this data from ice core things and you can correct for it, but you do need to know that. And there's also changes in the composition of CO2 which you might have to correct for as well. But that's the source of CO2 in all organic matter. And Jim talked a little bit about this. Here's the lipids, the lignins, the celluloses for carbon isotopes, and they all differ a bit. You all heard about C3, C4 yesterday, so I'm not going to go into that. There's only one, or I think only one C4 tree that I know of. So C3, C4 is not a big thing for tree ring issues. But again, if you're doing another kind of plant, you'd need to consider it. So what are the sources of water isotopes in tree rings? Well, all the source of hydrogen in organic matter comes from water. There's no other source. And all of that comes from basically meteoric water, however that comes, from Gabe and Jim's talk, rainfall, a water table, fog. I mean, there's all kinds of sources of water, but that's where it's coming from. Now, what happens to it? Well, it gets incorporated into organic matter with photosynthesis with this little guy right here. And if you may not remember from basic biology, but NADPH is the product of the light reactions, and that little H right there is stuck onto the growing organic matter. Remember that? Maybe not. Okay, but that's where it's coming from. Interestingly, the enzyme that makes this discriminates against deuterium drastically. The fractionation is between 120 to 171 per mil. Discrimination. So this H there is very depleted in hydrogen, and that's what's stuck on the organic matter. Once you've made the basic sugar from photosynthesis, then other things can happen to it. If you send it through glycolysis and lipids, there's a further fractionation, -30 to -60 for deuterium. Okay, so there's other things. But what I'm interested to talk today is about what we call post-photosynthetic carbohydrate metabolism, taking that simple sugar and making cellulose out of it. Now, if you didn't know what cellulose is, everybody know? Glucose, 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 glucose. It's all glucose, right? That's all it is. So it's a sugar. And it's just, so you'd basically take the sugar you made in photosynthesis and make cellulose out of it. Interestingly, there is an enrichment in deuterium. This fractionation is plus 144 to 166 per mil. Those are huge fractionation factors and, in these systems. Okay? So that's where the hydrogen comes from. No, it is used and can be used, and I'll show you why it's been changed, why people use oxygen more these days. There's a practical reason for that. Okay, sources of oxygen. Theoretically, oxygen could come from the oxygen in CO2 or the oxygen in water. Theoretically, right? Those two things. But all the oxygen in organic matter comes from water. All of it. Now, why? Because when the CO2 in order to be fixed has to go into solution. When CO2 goes into solution, it exchanges its oxygens with the water. Now, the interesting thing here is there's so much more water, a few orders of magnitude more water than there is CO2. So water swamps out the signal. De Niro and Epstein did this study where they had, I think, 2 terrariums with aquatic plants with known water source in both. They sealed them with labeled CO2, enriched and depleted CO2. And they let them do their thing. They measured the organic matter of the plants. The entire signal was the water. The label was gone, okay? Because it exchanged with the water. You get that? So all of our oxygen comes from the water. Now, this is a 27 per mil enrichment. And there's the little thing right there, 1.027, 27 per mil, with a little bit of variation. But these freshwater plants, wheats, tunicates, trees, there's all kinds of different organisms here, and they all have the same fractionation factor, 27 per mil, with some variation. What is that related to? Well, this is related to what we call the water-carbonyl interaction. So this is a carbonyl group. This is, the R's for organic matter. So the C double bond O is here, and a water molecule can exchange this to make two OH groups. Get rid of the double bond, two single covalent bonds, and two OH groups, and there's your label. Now, when it goes back to being a carbonyl group, so this goes back and forth, that label can stay. So the water labeled gets incorporated in organic matter this way. Seems pretty simple. That's how it's discovered. Now, I've been told by some chemists that there are other oxygen functional groups in organic matter that could theoretically exchange, but not at normal temperatures or pHs. They do have to have some bizarre condition for it to happen. This tends to be the critical feature for oxygen exchange with organic matter. Okay? And there's some other things here. This 27 per mil enrichment is valid and it's useful. But be careful whenever you say something's exactly 27 per mil. There's variation in it, and there can be some complications, especially when you get to very cold temperatures. And but generally we use the 27 per mil almost all the time. Okay? How do we analyze this? Well, the 13C is easy. You've all done this. It's the CNN analysis on the EA that you're all doing. You combust it in the presence of oxygen and make carbon dioxide and measure it. Right? Do I have to go over that? No. But you might not be familiar with how hydrogen is analyzed. The deuterium, the interesting thing about hydrogen analysis is that whenever you have a COH bond, that hydroxyl group, that hydrogen right there is exchangeable with any water it sees. Any water. It's the last water in the test tube that you put it in. It can exchange with that water. So that hydrogen there has no information about past climate. Right? The hydrogen that is covalently bonded directly to carbon does not exchange. So that is the hydrogen you want to keep to do your analysis. You want to get rid of that hydrogen. Got it? How do you get rid of that hydrogen? There are two ways. One is called an isotope equilibration technique, where you essentially expose your organic matter to a water of known isotopic composition. You let them exchange, you run the sample, and then you back calculate what it should have been, what the non-exchangeables should be. You understand? And there's some papers here if you're interested in how that works. What I've done more, and what a lot of people used to do, is called nitration. You substitute nitrate for that OH group. You just physically put a different thing on there that doesn't have any hydrogen, and then you run it. So that's called cellulose nitrate. And that's how we get rid of those. And that's why you have to get rid of them. Okay, so for oxygen, it's a little bit different. Oxygen, we use a pyrolysis system. For the carbon dioxide, you're using oxygen in terms of combustion. There's no oxygen to be applied to a pyrolysis. It's a very high temperature, glassy carbon, often column. And basically at high temperature, you're creating carbon monoxide. And that CO is then measured on the instrument. So you don't want oxygen in the system because that will screw up your isotope ratios of oxygen. And so this has shown to be pretty good. This is going to maybe your point over here. What used to be done to do oxygen was called a offline, one at a time, mercuric chloride offline pyrolysis. Whoa, nasty. Nasty chemicals, took forever, and no one liked to do it. So if you look at the older literature, everyone was doing cellulose nitrate. If you're looking at water isotopes, very few people were doing oxygen. But as soon as we found this online pyrolysis system, the newest literature, most everybody's doing oxygen. Why? Because nitration's a pain. So it's just practical. It's nothing. You get similar information from both isotopes because they're both isotopes of water, right? You might want to someday think about getting both hydrogen and oxygen because then you can do what's called, remember this, deuterium excess. You might want to look at that. But again, I don't do hydrogen very much anymore. It's just so much easier to do oxygen. I can run thousands of oxygen samples. So that's an issue. I also want to show a couple new papers. I don't really want to talk too much. These guys are arguing that they can get both carbon and oxygen off the same sample. Now they're doing a pyrolysis, so they're not doing combustion, but they're somehow back converting their carbon isotope ratios to account for the errors because you have glassy carbon in this thing. So there's a bit of magic going on here. I've talked with Todd and a few other isotopes, Craig and others, And some people are saying, I'm not exactly sure this works for some species, but not others. So I'm just pointing it out to you. It's there. Look at the papers if you want, but it's still a bit experimental. Okay? Brad, do you have any information about that? Or you never? Okay. Questions?
What kind of hydrogen do you want again? It's not the one that's attached to COH groups, but
The CH, covalently bonded to the carbon directly, not covalently bonded. This should say there in the notes, maybe they're too small, but the COH is not the hydrogen you want, the CH is the hydrogen you want. That make sense? The covalent bond doesn't exchange.
So you said that most of the hydrogen comes from water uptake through the roots, but that was in an experiment with a water plant, I guess. Does it vary if it's like a plant that's associated more with fog or something?
Okay, it doesn't matter. That's a question of source. Questions of source can be complicated. You can be in groundwater, soil water that's pre-evaporated, precipitation, fog. There's lots of different ways that you heard about getting water into the plant. But once it's in the plant, the rules apply. Okay, whatever the plant water is, it's that NADPH that's going to be depleted. And we'll talk about how you determine what leaf water is. That's a model, but that's what you're going to do. Yeah?
Which one is the C4 tree that you know of?
Oh, there's one in Hawaii. Does anybody know the name of the genus of the C4 tree? What's it? Halapepe. What a great name. What a cool name. Okay?